考试好了。现在还没有 live stream。
我已经开始。
已经开始了，有学生在吗？
有一个。
好 ，It's just a joke。你这样子拍得到这边？
可以拍的。
然后是这个加一样。
这个的话，你要自己调，可能是谁？
是因为以前 CH1 都不会点，然后这次有点，所以我在想说不要把
来最干净，收一个就好了。
一个，
收最干净。
这个有声音的。
Start. Alright, so now that we know dielectrics are somewhat imperfect metals, when we talk about its ability to form induced electric dipoles. For metals, we have a lot of free electrons. So basically, whenever you have external field line, you can induce one electron. And therefore, by making metal having no field inside. But dielectrics are not that good in terms of its electric dipole inducing capability. So in this example, I have 7 external field lines, but I can only induce 3 pairs of electric dipoles. So basically, inside the dielectric, the induced electric dipoles are meant to produce counteracting electric field intensity. So inside the dielectrics, we always suspect the field intensity, the amplitude, to be weaker as compared to my external field strength. So today we are going to try to find a way to mathematically formulate materials, dielectric materials, and we want to somehow compare, right, among different materials. So the first effort we're trying is to quantify the net electric dipole moment. So we're now trying to introduce a new vector field called the polarization vector, capitalized P with a vector sign. So this polarization vector is nothing more than the volume density of the sum of all the small dipole moments. So this non-capitalized P vector is the induced electric dipoles. So within every small value, you might have 10 pairs or 100 pairs of induced dipoles. They might be oriented in different directions. So the sum of all these induced electric dipole moments divided by your volume is thus defined as the polarization vector. So take a note on its unit. The polarization vector has a unit of Coulomb divided by meters squared. So you might be wondering, aren't it defined as the volume density? Why not divided by meter cubed? Because P is QD, right? Q has a unit of charge, Coulomb. D has a unit of meter. So basically you have meter, and then you have meter cubed. So 1 meter is being cancelled. So the unit for polarization vector is coulomb divided by meter squared. But the definition, the meaning is the value density. Okay? Having defined polarization vector, now we're going to talk about the effects of the induced electric dipoles in 2 aspects. So whenever we have a non-zero polarization vector, that is essentially giving rise to some new charge distributions. So the first one is we're going to talk about the so-called polarization charge density, rho P. The understood P denotes is due to the induced polarizations, and that can be viewed as a source of charge density. And then we're going to introduce a new vector field quantity. It's called the electric flux density, D, capitalized D vector. It is different from E. E is called electric field intensity, and D is called the flux density. The difference will be described in details later. But first, let's look at rho P. Whenever you have polarization vector having induced electric dipoles, you are contributing some effective charge density. And there are actually 2 forms. One is, well, whenever you polarize, right, by applying an external field, EXT, you somehow polarize or you align all these induced dipoles parallel to your externally applied field. So inside the material, things are all aligned, meaning it's polarized. So this P locally, each pair will be aligned, right, to your externally applied field. And each pair, even though your P is aligned in the direction of your externally applied field, but the field itself generated is reversed direction as compared to your externally applied field, right? So for this dielectric material, it has a finite size. Whenever the material has a finite size, you have boundaries. So in this case, on the top and the bottom, you have 2 surfaces. Okay? On the top surface, in the current case, because our externally applied field is pointing upwards, therefore making the top surface equivalently having positive surface charges deposited on the top. And on the other hand, for the bottom surface, it seems like I have induced a lot of negative charges. But overall, charge remains neutral, even though you have positive charges and negative charges, they sum up to 0, right? So dielectric materials tend to be charge neutral. Why do we have surface charge density? It's because we assumed in this case, this material is positioned in free space. In free space, you have nothing. So you don't have induced dipoles, right? And therefore, you have dielectric and you have free space forming the interface So along that surface, you have exposed charges. And therefore, whenever you have induced electric dipoles and you have the interface, you are trying to create effective surface charge density. Okay, so for the first case is we have surface charge density induced by the polarization vector. So now we want to quantify it. Suppose my material geometry is defined by the black line. So I have two surfaces, the top surface and the bottom surface. But it is possible that my externally applied field is having some angle to my geometry. Right? It's perfectly fine. I don't really need to apply my external field, which is parallel or orthogonal to my geometry. Right? It's fine. So in this case, I apply my field so the induced dipoles are all aligned to my applied field. But that is making some angle to my geometric surface, right? So my geometric surface is, this is my surface, so this is my surface normal. Meaning that each pair of the induced electric dipole is having some angle to my surface normal, right? So now I want to talk about how to properly mathematically formulate the resulting surface charge density due to the induced polarization dipoles. All right, so the total amount of charge over this surface, I can just form a box, right? A box with a surface area on the top and a very, very thin height. And I just calculate how much charge is being encompassed by that box. And not capitalized N is the charge density per volume multiplied by QD, that is how many induced electric dipoles are encompassed by my box. But since they are oriented in an angle with respect to my surface normal, I have to perform a dot product, right? And then multiply by my surface area. So that's the total amount of electric dipoles effectively pointing in the direction along my surface normal. Okay? But this NQD is just my polarization vector. By definition, NQD, right? Okay, so I can reform this equation as the amount of charge enclosed is my polarization vector, making a dot product to the surface normal, and then multiplied by the surface area. Then by definition, surface charge density is delta Q divided by delta S, right? And therefore, it is simply P dot surface normal. So this is assuming the polarization vector is parallel to your externally applied field, but somehow your externally applied field is making an angle to your material geometry. All you have to do is you apply the dot product. This is almost like saying E external making a dot product with your surface normal. So therefore, if you have some geometry and you apply your field orthogonal to the geometry, you don't create surface charge density, right? To maximize your induced surface charge density, you want to make your externally applied field parallel to your surface node. Okay? Again, the unit is Coulomb divided by meter squared. Okay? So this is the first time. Whenever you have induced electric dipole, you have the potential to create a new source of charge, and that is called the surface charge density due to your polarization, rho PS. S stands for surface. So this is true even though for this material, you have very uniform distribution. You have the same material, and locally, each point, you have dipoles. So even though inside the material, as a bulk, it appears to be charge neutral, but at the surface, you have the presence of the surface charge density. So the next terminology we're going to introduce is the bulk, the volume charge density. Is it possible that just by inducing dipoles, as a whole, we look from the macroscopic view, the material appears to be charged? Is it possible? Let's look at this case. So we have some material, right? We have a very big material, and we're now looking at the microscopic view. This material is actually having maybe two different components. For example, salt and sugar. Is it possible? Of course, yeah, you can always drink salt plus sugar, right? You can just drink it. When we apply an external field, the ability to generate induced electric dipoles for salt and sugar are different. So in this case, the top material is more sensitive. It can induce more electric dipoles as compared to the bottom material. Okay? So for this case, as a material on the bulk, on the macroscopic view, because I have different materials making up this matter, I have some net charge within the material. And that is the origin of the volume polarization charge density. So this is telling you, if I have multiple components making up this material, I have an inhomogeneous material. Then, inside the material, I can always expect to find net charges. All right? It's because we have incomplete cancellation. So the net charge does not go to zero, right? Because we're dealing with an inhomogeneous material. Inhomogeneous. Meaning, the polarization factor for one point can be different from the polarization factor of another point. Therefore, this P is a function of space. But in the previous case, we have homogeneous material. So for each location, we have the same polarization factor. So basically, in this case, the polarization vector P is a constant. It's not a function of space. All right? So whenever your P is a function of space, you're dealing with an inhomogeneous material, and therefore, inside the material, you have a way to form the volume charge density. Okay? Now, mathematically, all we have to do is we find the surface charge densities, the sum of the surface charge densities, and then we multiply by -1 to find this net volume charge density. Why? Look at this case. For each material, the charge remains neutral, right? Meaning, on the top surface, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positive charges. On the bottom of my material number 1, I have 8 negative charges. So for this given substance itself is charge neutral. And also for this case, I have 4 positive charges and 4 negative charges. So this P2 itself appears as charge neutral. This P1 appears as charge neutral. But looking as a whole, these two together, right? On the top, I have 8 positive charges, but on the bottom, I only have 4 negative charges. So I sum all the surface charges up, I have 4 positive charges. But I still need to remain charge neutrality, so the only chance is inside, I have 4 negative charges. Okay? So that's one way to look at it. Another way to look at it is the net charge is not 0 because on the bottom of my material number 1, I have 8 negative charges. On the top of material number 2, I have 4 positive charges. These two adds up to 4 negative charges. Okay? Same result, but looking from 2 different perspectives. All right, so all we have to do is, well, suppose we don't want to enter this material, we only want to observe it from the outside. So we count on the total number of charge at the outer surface. So QPS1 is this one, the 8 positive charges. QPS2 are the 4 negative charges. So I sum them up. And due to my understanding, it's just P dot AM, but this P for this one is P1, for this one is P2. Okay? This is like Gauss's law. It's exactly Gauss's law. Right? Over the closed surface, I'm trying to evaluate the total polarization vector, making a dot product to the surface normal. Okay? And then I can have this one, the integration over a closed surface, making the equality to the divergence of P over the entire volume. Do you know why I can draw the equality? You just finished your examination, but you're not getting away from divergence theory. This is where we can invoke divergence theory. Okay? Initially, you have surface integration over the closed surface, and now we transform to volume integration. And somehow we can relate divergence P to the volume charge density. Because by default, if I integrate over an entire volume. I have some net charge. That means I have non-zero volume charge density. Okay, so in this case, my QP, the net charge, is the sum of my two surface charges, but I have to multiply by a negative sign to maintain charge neutrality. Okay, so I need to take account of the negative sign. And that is simply negative divergence P. Okay, so in this case, whenever we're dealing with inhomogeneous material, meaning polarization vector itself is a function of space, then we perform its divergence and we multiply by a negative sign, we have the resulting volume charge density. Think about it. Is it making sense? Why do we have a non-zero volume charge density due to polarization? It's because we know that we're dealing with inhomogeneous material. For inhomogeneous material, polarization vector can be very different for different locations, right? And that is telling you this P vector is a function of space. Therefore, whenever we're trying to perform divergence, we're trying to calculate the differentiations of P, right, in different unit vectors. In Cartesian coordinate, X, Y, and Z, you're all trying to find their changes, right? It makes perfect sense. If P is not a function of space, meaning you're dealing with a uniform material, P is a constant. Divergence of P in that case is 0, right? So whenever you're having a homogeneous material, you don't have volume charge density, okay? So you have to be able to connect these dots together to form a line, so your understanding is deeper and more thorough, right? Okay, but basically, this is telling you whenever we have dielectrics, we apply external field, we induce electric dipoles, and the induced dipoles effectively give you, for homogeneous material, they give you polarization, surface charge densities, simply P dot AN, the surface normal. And if you have inhomogeneous material, those induced electric dipoles end up giving you effectively some volume charge density, negative divergence of P. From our understanding to Coulomb's law or Gauss's law, whenever you have non-zero charge distribution, those charge distribution creates its own field distribution, right? So you're free to replace all these charges, right, into Coulomb's law formulation or Gauss's law formulation. So this is telling you, once you have induced electric dipoles, they create their own field distributions. So you need to calculate them. And that's making things more complicated, right? You must be thinking, oh, I have externally applied field, which I need to calculate, and I have material, I have to calculate everything, because once I have induced dipoles, I have to calculate their resulting field distribution. That's very tedious. And you want to drop this class. I can imagine your frustration, but in the upcoming slide, I'm going to tell you things are not so complicated. We're smart, right? We can find a way to quantify dielectric materials in a very simple sense. All right, so bear with me. And this is the point why we want to define a new vector field quantity, flux density, capitalized D. Okay. And it only makes sense to talk about D whenever you have materials. For vacuum, you don't really care. You only care about E, the electric field intensity. But once you have materials, we talk about this D. Okay. So I am going to define D, but I want to make a discussion which makes more physical sense. The meaning of flux density and the difference as compared to electric field intensity. Okay? So let's come back to the very first fundamental postulate when we talked about E field intensity. So we first talked about the divergence of E is equal to rho divided by epsilon 0, right? Initially, we didn't talk about what type of charge density was related to E. But now I'm telling you, when we are in free space, right? We're in free space, in vacuum. Vacuum is defined as nothing, right? So if you want to create some field distribution in vacuum, that has to come from free charges. This is the best way for you to remember it and understand it, right? Vacuum has nothing. So if you can create some field line, it's definitely coming from free charges. So divergence of E in free space is basically coming from free charge densities. They're free. But now we're talking about materials, and especially dielectric materials. Whenever you have matter, you have atoms, you have molecules, you have the ability to create induced dipoles, right? So in this case, when we're talking about dielectric medium, divergence of E is no longer just comprised of the free charge densities, but we also need to take account of the charge densities created by the polarization factors. Okay? Remember, we spent so much time talking about what the electric dipoles do. They provide additional charge densities. And we now know how to formulate these charge densities. So inside the material, you need to add the polarization-induced densities, charge densities, to the free charge densities. Right? So basically, when we're talking about matter, dielectrics, divergence of E is rho total, the total charge densities divided by epsilon 0. Okay? So another way for you to remember is, this is the real generalized expression. But when you are going into free space, you have no way to induce electric dipoles. So rho p is always 0 for vacuum, and therefore you have the first fundamental postulate. Okay? But now that we know from the previous page, rho p is equal to negative divergence of polarization factor. Okay? So now we have one divergence and we have a second divergence. Why not combine the divergence to one side to make everything simple? We can do that. We can only multiply this epsilon 0 is a constant. We can just multiply it to the left-hand side. And divergence is distributive. We can combine these two into the divergence, right? So now it reads divergence of epsilon 0 E vector plus P vector is equal to rho free. So why not define the sum of these two vectors as a new vector? So it's easier for you to write. So why don't we define this P, a new vector field, as epsilon 0 E vector plus P vector? So you don't have to write so many things. Okay. Now, by this definition, divergence of D, this D is called the flux density. The electric flux density is a vector. It's equal to rho free. So at this moment, think hard. I mean, what's the difference between D and E? What's the difference? While you're thinking very hard, let me just try to write it for you. So divergence of D is equal to rho free. On the other hand, divergence of E is equal to, use another color, rho net divided by the constant. So take a good look at these two formulas. It's telling you this D vector is directly associated only with the free charge densities. Like you have free charges in space. So inside the material, this D is related to only the free charge, but E is related to the total charge. Okay? This net charge is the sum of free charge density plus the polarization charge density. Right? Now, before I go on, take a guess on which field quantity can be smaller. Take a good guess. If I only care about the amplitude of D as compared to the amplitude of E, if I don't care about this constant, which one can be smaller? When I was a student, I looked at this definition, and because I don't care about epsilon 0, rho free plus rho p, right? My instinct was to say, well, because the net charge density is the sum of the free charge density, this guy, plus some additional value, the primation charge density. So this adds up to a larger value. So initially I assume, if I don't care about epsilon 0, okay? If I don't care about epsilon 0. It seems this mathematical formula can be misleading. Because you think, oh, you add additional charge densities. So this guy is stronger. Is that true? We can skip this. Okay, we can skip this one. Let's come back to the picture. Remember, as I talked over and over repeatedly, we have a given dielectric material within this black lines, and we apply external fields. You can imagine the externally applied field is the result of free charges, right? Because in vacuum, you want to create field, you have to have free charges. And these free charges create the externally applied field lines, and they induce electric dipoles inside the material. And as we talked about, whenever we have induced dipoles along the surface, we create induced surface charge densities, assuming this is a homogeneous material. So now we count the number of charges for this surface. Initially, I have 8 positive free charges, but now I have induced dipoles, so I have to subtract 3 negative charge. So basically, rho free plus rho p is reduced. This is actually a reduced amount of charge. It's also true here for the bottom surface. Initially, I have 8 negative charges, but somehow due to the existence of the induced electric dipole, I have 3 positive charges on the bottom surface. So these adds up to a smaller absolute value quantity. This is in perfect accordance to the fact that field lines generated by the dipole is used to counteract the externally applied field. Okay? So don't be fooled by this plus sign. You are actually adding a negative quantity. All right? So in the end, E is related to the net charge density. So you only have, 5 net charges on the top surface. So basically, try to remember and try to understand. I repeat, dielectric materials give rise to induced electric dipoles for only one purpose. They want to make the field strength inside the material weaker as compared to your externally applied field. So this E absolute value is smaller than D. Okay, we don't care about this constant, okay, for now. Induced dipoles are there to make the field strength inside the material weaker. So do not be fooled by this plus sign. Okay? Because this plus, if you have positive free charge, you are adding a negative charge density, effectively making E smaller, weaker. Right? Okay, so the better way, the very simple way, now that we know this phenomenon from a pictorial way, so now it's math. We can somehow formulate, well, because we know that the dipoles are aligned in the direction of my externally applied field. So somehow P, the vector, the polarization vector, is also aligned to my external field, right? And then we have some scaling. So depending on different material, this chi is called the electric susceptibility, chi E. How good is this material capable of giving rise to electric dipoles? If you have a very high chi E value for a given material, this material is very sensitive. So you apply some external field, it produces a lot of dipoles. Right? Vacuum has 0 chi E because vacuum has nothing. You cannot contribute to electric dipoles. Right? So in another sense, metal has a very huge chi E. It's almost infinite, right? So now we have P equals epsilon 0 chi E times the E, external field, right? We can just replace this P by epsilon 0 chi E. So basically, the flux density, which is associated to free charge density, can now be formulated as epsilon 0, 1 plus chi E times the E vector. And we call this 1 plus chi E as the relative permittivity of that given dielectric material. Right? So this is very easy. For any given material, somebody measured its capability of generating induced electric dipole, and that is coined or quantified by this chi E value. Or together, 1 plus chi E is this relative permittivity. For example, for water, chi relative H2O is 1.33 squared. Epsilon R, glass, is 1.5 roughly squared. Okay? So in the future, I mean, you only look for this relative permittivity, and you can just calculate, or you can understand, you can classify the material response. Okay? So all dielectric responses are somehow represented fully by this relative permittivity. It's a constant. Once you know its operational frequency, it's just one constant. So you no longer need to take care of all these and not even this. Okay. You don't really need to calculate the field distribution or potential distribution due to the induced charge densities. Everything is represented by that simple constant. Okay. Well, sometimes people try to combine epsilon 0 times epsilon r, and we define it as the absolute permittivity. Okay. So basically, B equals epsilon 0 times epsilon r, E, but sometimes you're even lazier than that. You want to combine epsilon 0 times epsilon r as one single variable, epsilon, and that single epsilon is called the absolute permittivity. Okay? Now, again, the very last minute, the most important message of wisdom. D equals epsilon E. Again, this is a confusing formula. When I was a student, I thought, oh, if I have a material with very high epsilon value, a very high epsilon value means what? Means this material is very capable of generating induced electric dipoles, right? So I thought, oh, if I have a material with very high epsilon, that is making its D very big. Is it right? Think about it. Is it right? D is only related to the free charge density. So even though you have different materials positioned in space with the same applied external field, D remains to be a constant. Okay? So my suggestion for you is try to remember this relation between D and E in a different way. This expression, E vector, is a flux density vector divided by epsilon. This is making more physical sense. It's the same equation written in a different way, but now this is telling you there's no room for ambiguity. If you have a material with very high epsilon value, it's making your field strength in terms of E field intensity, which is associated with the net charge density, to be weak, right? So this writing formulation is telling you D should be held as a constant because it's only related to free charge density. E is related to the net charge density. So the difference is, for different material, you have different ability to form induced dipoles. If you have a material very capable of producing induced charge density, induced dipoles, then you have a very high epsilon value. And the sole purpose to have induced electric dipole is to counteract your externally applied field, and therefore making the E intensity weak, right? So this is a more proper way to write down this formulation. Very high epsilon, you have lots and lots of electric dipoles, and making your resulting E field intensity weak. So one final test to your understanding. If I use this formula and I want to describe metal, what should the epsilon value for metal be? Inside the metal, you have no E field intensity. So this, in terms of this absolute value for metal, epsilon reaches infinity, right? And that is in accordance to our understanding. Metal is the material for perfect induced electric dipoles. All right, so let's conclude here.